Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our finite element analysis and design software, RFEM. The topic for today's webinar is Introduction to the FEA program RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Stefan Frenzel will be your moderator today, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So regarding the content for the next hour today, today's presentation is the first part of a three-part webinar series happening this summer. So today we'll be focusing on the basics of the FEA program geared towards completely new users. Our second webinar will focus on a few more advanced features within the program, and the third webinar will be regarding BIM integration. So I will explain RFEM, which is our main finite element analysis program, and the add-on module concept used for design. Then we'll move into our example where I'll give an introduction to the modeling, the loading, setting up our load combinations, and finally we'll run a full analysis and take a look at those results. Then I'll give you an introduction into a couple of the add-on modules, including RF-STEEL AISC and RF concrete members. We'll take a look at how the program will design our structure and what these results look like. And finally, we'll touch on our printout report options within the program. So RFEM is the main finite element analysis program. What this allows us to do is to fully model our structure. So within the program, we would see all the cross sections, the materials from the various standards, including the AISC, the CSA standard, as well as many other international standards. And we can model members, surfaces, and solids. We also have included BIM integration, so you could integrate with AutoCAD, Tekla, Revit, STP files, STEP files, IFC, and many other file extension types. And we will set up the loading and set up the loading combinations within the main program according to the various standards as well. And we can run a full analysis. Now, with the analysis, we would get information such as deflections, support reactions, internal forces, and we can take this information into our own design tools such as spreadsheets. Maybe we have some in-house programs to do the design for us. Now, on the other hand, if we want to do design within RFEM, we would utilize what's called our add-on modules. So you can see that I have listed a handful of add-on modules here, which actually doesn't complete the full list that we have. But overall, we have steel, concrete, wood, we have aluminum design. Some of those more niche markets that we have would be cross-laminated timber design. We can do glass design for single layer laminated and insulated glass. We have fabric form finding, so for tensile fabric structures and cable elements, because we are a nonlinear analysis program, we have these capabilities as well. Now, the nice thing about these add-on modules is you don't necessarily have to purchase all of them. You would purely purchase the modules that you use for your particular projects in your design based on the materials or maybe the standards of the country you're located in. So that keeps the software affordable and really cater to your individual design needs. So with that, we can move into our example today. When we launch RFEM for the first time, we're presented with this dialog box. We do need to give it a name, so we'll just call this one intro. The type of model can be a three-dimensional model by default, but you also can set it to 2 dimensions if you'd like. The orientation of the global z-axis is by default set to upward. When we expand these detail settings here, I would suggest to set the local axes of the surfaces and the members to downward. This is important for concrete design. We can generate load combinations automatically. So you can see here within this drop-down box, you'll find the ASCE 7 2016, the NBC 2015, as well as many other international standards. So when we have this option checked, the program will automatically generate all of those load combinations. We can uncheck this to manually create the load combinations instead. If you are looking to access some of the older standards, you can push this button on the right-hand side, and now within this drop-down, we'll find all of the older ASCE 7 load combinations, for example. So moving forward with the 2016, we click OK, and we're immediately brought into our main program, RFEM. So we have our graphical interface within the main window here. So as we begin to generate this model, of course, we'll be doing so within this main window. We do have the tables to work with down at the bottom. Now, what's beneficial about here is if you prefer to not draw in members and nodes, you can do so within the table. You also can import in directly from Microsoft Excel. So perhaps you have all of the nodes specified in a spreadsheet type format in Excel. You can, at the click of a button, import those into RFEM, and everything will be automatically generated in our graphical window. Up at the top, we have our quick tools. Keep in mind that these are completely customizable as well. So over 1,800 different buttons within the program that we can really cater to whatever setup that you would like, and you can rearrange them however. Over on the left, we have what's called our project navigator, and I like to think that this is a little bit more unique to our program RFEM. As we begin to generate this model here, all of our input data is going to be available in these various trees. What this allows us to do is to quickly make changes to entire cross sections. Maybe we want to change an entire material without having to do it individually within the graphical interface here. If we scroll a little bit further, this is our long list of add-on modules. So you can see why we have the concept only pay for what you use, because essentially you'll probably end up using relatively few of these for your specific design projects. Under the Display tab, this is going to control everything that we're viewing graphically here. We can turn on and off elements. A little bit later, we'll get into this results tree here so that we can change around exactly how we're viewing our results graphically. On the Views tab, it's empty right now, but we can create some user-defined views to quickly access them. And as we begin to generate the model, the program will come up with quite a few default view types as well. So to begin today, I want to right-click down at the bottom of the screen under Grid. I want to edit the grid, and right now the default spacing is set to 1 foot, which that's entirely okay. You can increase that or decrease that. I do want to increase the number of grid points on either side of the origin and set this at 100 because our structure is fairly big today. The object snap is exactly what it sounds like in comparison to AutoCAD. You can set midpoints, quarter points, parallel, partition points. Those are all available within this object snap tab. The guidelines would be project grid lines. That might be beneficial for column lines, for example, for a larger building structure. Background layers, we can import in DXF layers. This includes multiple layers at different elevations as possible as well. And finally, line grids. This might be beneficial to create a new line grid. It's a 3-dimensional option here. So instead of a 2D drawing grid, which we see in the background here, you actually have the option to create a spherical, cylindrical, inclined, or Cartesian 3D drawing grid. Okay, so once we have adjusted our drawing grid, you can see it's slightly larger now. So we'll begin by drawing our first surface element. And I go up here to my quick tools and I'm going to access a new surface. Now you'll notice that we have many different shapes here, so you don't necessarily have to draw a simple rectangular surface, but we have circles, semicircles, you can draw your own with a polygon. So really no limitations here. We do start off today with a typical rectangular surface. Now the material by default when you first install the program is 4,000 psi concrete. You always can access the material library here to set a different material. So you'll notice we have our filters over on the left where we can filter to concrete, to wood, to metal, and then Right here under the standard group, we can select the ACI. For example, we have the CSA standard if we would like to choose a different material under one of these different filter settings. One thing to take advantage of is what's called a favorites group. So you can create a new favorites group here, which will allow you to turn on and off all of these different materials. So that way you're not having to reset these filters every time or to scroll through long lists, but rather just activate the favorites group and then utilize that from there on. So today we will just be using 4,000 psi concrete. I set the thickness of my surface to 12 inches. The stiffness type is set to standard, so this would just mean that we have the same stiffness in both the local X and Y direction. Under this drop down, something else to point out that we do have orthotropic stiffness, so you can see a few of these different types here. When we edit the expanded settings, this will bring us into the surface type orthotropic. From here, we can choose one of these different options, such as hollow core slab, for example, where all we need to do is to enter in a little bit of dimensions. The program will automatically calculate the stiffness matrix for us, and we can actually view it within the program. So quite a few options, such as a waffle slab, a trapezoidal sheet for maybe a ribbed metal roof. So you can select those here if your stiffness is varying in two directions. For today, we're sticking with the standard stiffness, and we click OK. My first point that I'm going to click is at the origin, and then I'm going to set my first surface at 40 feet in length and 25 feet in width. My second surface begins where I ended that previous surface, and we're going to snap to a point here that is 40 feet wide again and 23 feet in width. So the surface over on the left, I'd actually like to extend it out in a semicircle in the front. So how I can do this is just by drawing a new line element. Now a line element makes up the boundaries of these surfaces. So I can go up here to my tool to choose a new line. Now, again, similar to AutoCAD, of course, we have just straight lines, but you'll see here many other options such as arcs, polylines, splines, circles, so relatively few limitations when it comes to complex geometries. We will select the arc, and we will click on the left point of our slab on the left to the right point. Now, my third click can be anywhere within the project grid here to define my radius, or I can simply type in 13.5 feet on my keyboard for my radius, and I hit enter. And so now you can see that arc was generated here. So using my selection box, I can highlight only the front line here and the surface. I hit delete on my keyboard and I'm left with the exterior boundary lines. So I go back to draw a new surface and I'm going to choose the option here to select boundary lines. All of my settings are previously pulled up from my previous surface. I click OK. I make a couple clicks and the program automatically determines what the exterior boundary line should be. So now we have completed the surface on the left. The next step would be to add some columns extending from the slab down to our foundation. And I find it a little bit more useful here to zoom in and to turn this into wireframe view instead. I'm going to draw new nodes within the surface. So I go up to my drawing toolbar here, I click new node, and because my drawing grid is located at the same elevation, this just simply allows me to draw some nodes and snap to the drawing grid points here in order to add these new nodes directly onto my model. We're going to add a few more in the rear here, about 3 feet away from the surface edge. Okay, so once we have completed these nodes, I want to draw a new member. Right next to the line element is the option to draw a new single member. The member type by default is set to beam. So a beam is just anything that's a typical beam, a typical column, but you'll notice many other member types available to us here, such as tension only, compression only. We do have cable elements because we are a nonlinear analysis program. We will visit rib elements in just a minute, but for our columns, we'll leave this as a typical beam. We want to generate a new cross-section, so we access our cross-section library. When I access the cross-section library, you can see here that my rolled sections and built-up sections are available on the left. So this will have the availability to pull open all the different sections from the AISC standard, the CSA, Eurocode, many other different options there, which we'll visit a little bit later on when we get to our STEEL members. The rest of the members here are parametric. So what that means is that we can simply type in the dimensions of the cross-section and the program will automatically calculate all the cross-section properties for us. So that includes our parametric massive section for our concrete column, and we will set this to 15 by 15 inches. The material is also set here. We still want to utilize 4,000 PSI concrete, but you can always access your material library to change or add a different material. I click OK. Keep in mind that the member hinges or the member end releases are also defined within this same dialog box. So when we have this set to none, that means that the member will be fully fixed. But we always can create a new member end fixity here, and you'll see our 6 degrees of freedom. The program automatically assumes that we probably want to release the moment in the local Y and local Z directions. We also have partial fixity here, and we can take advantage of the geometric nonlinearity within the program, such as plastic hinges, slotted joints. Maybe you want to define your own partial activity. That's all possible with those nonlinear options. For today, we want our columns to be fully fixed, so we'll leave these set to none. So when I click OK, I do have the option to maybe change around my drawing grid orientation here and to snap from one point down to the other. But instead, I'm going to utilize this feature within my small dialog box where I can define the length and the direction of my member. So I know my column height should be 15 feet, and I want to define these perpendicular to the work plane in the negative direction. So now what this allows me to do is to snap to those nodes that I've just created, and essentially I don't need to define the length and the direction because it's automatically done for me. So we can turn this into rendered view to see a little bit better view of this. So now we have all of our columns framing into the slab on the left-hand side. Now I'd like to make a copy of all these columns and this slab to the other side as well. So of course we can use the Move Copy tool, but we also have a mirror tool within the program, again similar to what we'd see in AutoCAD. I can highlight my slab on the left-hand side, including all of my column elements, and we can see that they are highlighted in red, and I utilize my mirror tool up at the top of the screen. For this, I can create a copy. I'm going to mirror about the global YZ plane, and then I can just simply click a point on my model to mirror about. Now, because of those snap settings, the program recognizes what's the midpoint of this center slab here. The coordinates are automatically populated. I click OK, and now you can see the slab element generated on the other side. Okay, so we'd also like to add in an opening to the center slab. We eventually want to add on a second level story, so we need some type of opening for a stairwell, for example. With the openings, it's located right next to my surface. And again, we have just rectangular openings, but you'll find many other opening shapes in here. So semicircles, circles, L shapes, or you can draw your own with a polygon. For today, we will utilize just a rectangular shape, and it might be a little bit beneficial here because this is a little bit difficult for you guys to see, to turn this into wireframe view. And I'll just simply snap one point on my drawing grid to the other point, and now we see this opening generated. Turning it back into rendered view, we can see it even better. So this is a pretty long span for our center slab here. What I'd like to do next is to draw what's called rib elements. These rib elements will be dropped below this slab, spanning from my columns on my left to my columns on my right. Now, rib elements are drawn slightly different. We need to first define the line and then assign a rib cross-section to it. So underneath every member is a line element, and we can see that when we right-click, we have the option to either edit the line or edit the member. So I can go back to drawing a new line, similar to what we saw before. This will just be a straight line, and I choose from the left column, and I snap to my right column. I right-click once, and I do the same exact procedure for my second set of columns here, and then I can right-click twice to exit that dialog box. So now you can see just simple line elements. They're not adding any stiffness to my structure. It's purely just a drawing element. I do want to utilize this feature up here called Connect Lines or Members. What this allows me to do is to highlight over my structure, and in particular, I'm focusing on those line elements that I just generated. This will simply create a node at those intersections and break those line elements apart. So now I go to draw a new member again. This time though, the member type is going to be set to rib. I don't want to utilize the column cross-section, so we need to create a new cross-section once again, and we'll utilize this parametric massive shape. And the dimensions here will be 10 inches by 20 inches, still 4,000 psi concrete. Under the rib settings, we do need to specify here that we would like to drop the rib below the surface. Well, the program can automatically do this. You'll notice this little picture updates when we choose on the positive Z side of the surface. So the program will automatically place those little rigid links at every FE mesh point to drop that beam below the thickness of our surface. The program can also auto-detect the effective width and which surface that should belong to. Now, we do need to specify the effective width distance. That can be set to L/6, L/8, or we can manually enter it in as 3 feet, for example, on either side. So when I click OK, I just need to simply click on these line elements that I just generated. So we do so at the front of the structure, and we do so at the rear of the structure. And now you can see those rib elements dropped below the thickness of that surface to support that slab spanning from column to column. Okay, so we are now complete with our first level here, and we would like to create a second level. It actually is going to be almost identical to what we're seeing here. So an easy way to replicate our first level is just to highlight everything with my dialog or with my selection box, and I can zoom in, hold down my control key on my keyboard. I grab my bottom left node here, and I can utilize what's called our drag and drop feature. So the drag and drop feature is very useful for quickly making a copy, or you can move something with the drag and drop by not holding down the control key. Now we have an identical copy for our second level here. What I would like to do is to delete this opening, so all I need to do is to highlight it graphically. I hit delete on my keyboard, and I'm just left with the boundary line elements and nodes. I even can hold down my control key to select those two nodes, hit delete on my keyboard to clean that up a little bit further. So the next thing we'd like to do is to create a couple of steel trusses spanning in my second level opening here, maybe to support our roof deck. Well, we typically could go in to draw a new member. This time we change a cross section and material to steel. But we also, under the tools option, have some model generators here. So within the generate models for members, or you can utilize surfaces as well, but under members we have 2D trusses, 3D trusses, 3D halls. We even have a stairway generator. So this is just a way to take advantage of the program automatically generating these elements for us. So today we'll utilize this 2D truss option. Up pops my dialog box, and I just need to specify the type of 2D truss. So we'll select a flat truss from our list. We also can specify the way that our diagonals are laid out, or our web members. We set the number of bays to 6 total. The total length, if by chance I don't know what this span is right off chance, no problem. What we can utilize is this arrow over on the right and to choose the measure function. With the measure function, I'm brought back into RFEM and I can left click on the left side of the structure and click on the right side of the structure, and the program will automatically measure that for me as a total of 40 feet. I need to specify the depth of the truss as 3.5 feet, and then the first span is set here by simply taking the 40 feet divided by the total number of bays, so you can adjust that if you see it necessary. Now you'll notice that my cross sections are also set here for my cord and web members. We've only defined concrete in the model so far, so we certainly don't want to create a concrete truss here, but rather we'd like to access our cross section library. So we pull this up, and this is exactly the same dialog box that we've seen before. This time though, we want to pull up our I rolled sections. So over on the left, we have again our filters. We can specify the AISC. You'll see here the CSA standard. Again, many of those international standards. So if you have an international project, all of these cross sections and materials will automatically be included within RFEM. Moving forward with the AISC, you can see the long list of W shapes available to us here. Again, we can utilize a favorites group if we want to just add a few cross sections to a favorites list that we utilize quite often, so we're not having to filter through this long list every time. For today, I will choose a W8 by 28 for my top and bottom cord. The material, by default, the second material is going to be A992 when you first install the program, but again, you can always access your material database here to find all the other steel materials available to us. I click OK, and we are presented with our cross-section parameters here. I click OK once again, and now we can see that W8 by 28 is available to us. Well, we can now specify that for the lower cord as well. As far as the diagonals, same concept. I just simply want to go back to my cross-section library, my rolled sections, and this time I want to choose a smaller section, a W4 by 13. I click OK. So we want to set this as the cross section for both web members here. Now you'll see all W sections specified for our cord and web elements. Now the member type, you can see that again for the upper and lower cord, we have this set to beam. But for the web members, we have it set to truss. Truss is going to automatically apply a moment and release on either end of the element. So it's just a simple application rather than having to manually go in and apply that moment release. We also have a truss option where only axial forces are transferred, so releasing both shear and moment. So once we have defined our cross sections, we want to choose the left node graphically, which is populated as node number 42, and the right node to where we would like to place the truss, and then you can see that steel truss is automatically placed within our structure. A helpful feature under the display tab, we can scroll all the way down to the bottom and we can change the colors and graphics according to the member type. What this allows me to see here is which members are defined as beam elements. We can see our rib members denoted by the pink color here, as well as our web elements denoted by the truss. So these two exterior web members, I'd actually like to hold down my control key and select both of them. I can double click to edit, and I'd like to change the member type here to beam instead. So I don't want to apply that moment end release, rather we'll make those fully fixed. So now I have my truss generated entirely. I can use my selection box to select this truss, take advantage of my move copy tool, and I'll make one copy in the global Y direction of 8.5 feet. I click OK, and now we have a second truss generated. So this almost completes our modeling. The final couple things to take care of would be number one, the support conditions. We have nodal supports up here in our toolbar. We have line supports, which may be applied to the bottom of walls, for example. We have surface supports. So this might be beneficial for a surface slab on grade where we can define the soil properties and then the program will apply spring stiffnesses for us. For today, we want to utilize the new nodal support. We do have a few default options in here, including a hinge type application, as well as a rigid support. We can always create our own as well. Now, this dialog box should look fairly familiar because we saw almost the same layout for our member end releases. We have 6 degrees of freedom where we can fully release or fully fix these, partial fixity here. And then again, those geometric nonlinearities within the program allow us to set friction supports, partial activity, yielding, tearing are all possible within these nonlinear options. For today, taking advantage of the fully rigid support, I can click OK. And I orient my model here to drag my selection box across the bottom of the model to apply the fixed nodal supports there. Okay, so the final thing to do before loading is under Calculate FE Mesh settings. The default FE mesh length is set to 1 foot. Now, if we're working with a much smaller scale model, maybe a finite element of a connection, then we obviously need to change this to something much smaller. For today, 1 foot is adequate. We also can choose this option here to regenerate the FE mesh. All that this allows me to do is the program quickly generates the FE mesh. I turn this into wireframe view, and you can see that the FE mesh was generated automatically, taking into account all members, all nodes, openings. We don't have to manually submesh any of these elements. The program does everything automatically. And in the second webinar series, I'll get into features such as FE mesh refinements about particular nodes. Now, every time you run a calculation, the program will mesh the structure for us. So we don't have to generate this FE mesh. I just wanted to show you guys what was going on in the background. Okay, so moving on to loading here, we create a new load case, and this brings up our load case and combination dialog box. The first load case description will be dead load with the action category set to dead. Now, action categories are important because it tells the program which load factors per the ASCE 7 standard to apply to which load cases. Self-weight is automatically activated here with this checkbox with -1 in the global Z direction. We create a new load case and we will set this to live with the action category of live. Notice self-weight is unchecked here because we don't want to account for self-weight twice. Finally, our third load case for our simple example today will be a wind load for a lateral load with the action category set to wind. So in reality, for a true structure, you'll have many more load cases here, including different wind load combinations, and those will all work together under this actions category. But our example today is quite simple, so we only have 3 different load cases. Under the combination expressions, the program will generate both the LRFD load combinations and ASD. If we're just curious to see what these look like directly from the standard, we can click this little info button to see them listed out directly here. The Load Combinations tab will actually show us the true LRFD load combinations and ASD load combinations relevant for our model based on the load cases that we've defined. So we're not having to sift through multiple load combinations for load cases that aren't relevant. Finally, the result combination here is going to be an envelope solution. So the program automatically creates 2 result combinations. The first would be our LRFD load combinations, and the second would be our ASD load combinations. The program will take into consideration all of these load combinations and present us with the max and min forces, deflection, support reactions. So as I said, it's an envelope solution for all of these load combinations considered. So now that we have set up our load cases and combinations, they're available to us within our drop-down box here. But we need to actually apply the loads to the structure. So we have dead load selected here. And I'm going to utilize a new surface load up in my toolbar. I click this option and my dialog box allows me to specify the load direction, so we'll set this as the global Z. The magnitude here is going to be set at negative 0.03 kips per square foot. I click OK, and then I just need to simply highlight over my surfaces on my second level, and I can highlight over my surfaces on my first level. You can see the program automatically accounts for the openings, and the surface load is presented to us here for dead load. So now that we have added these surface loads, we also need to account for our members that we have created with the steel truss, because you'll notice that these surface loads have not affected these steel members at all. So what we'll need to do is to go up here to our toolbar once again to access a new member load. Now this is not to be confused with the tool right next to it called new line load. Line loads are for surface elements. We want to choose this option, new member load, and similar to the surface load, we'll see here our dialog box. We specify the load direction in the global Z direction, and we specify a magnitude here of negative 0.43 kips per foot. The load distribution will be uniform across the entire length of the member. So now I can click OK, and you'll notice here that I can just simply click on the top chords of all these members. If we have a little bit difficulty seeing this, we can always switch around our view here, and maybe we zoom in a little bit further and we continue, or actually I just lost that dialog box, but we can right click to choose repeat new member load. Again, all of our settings are remembered. I click OK, and then I continue to click the top of these members here. So now that we have completed the member loads, you'll notice that they'll now be displayed along with the surface elements shown within the model here. So now we want to move on to our next load case. Now for live load, we'll follow the same procedure for our first floor here. So we can create a new surface load once again. In the global Z direction, the only thing I'm going to change is the magnitude at negative 0.1 kips per square feet. I click OK, and I can highlight my selection box over that first level. Now for the second level, I want to maybe assume that I don't want to apply a live load at the entire surface element. Rather, maybe we have some type of corridor here where maintenance can access the roof equipment. So we'd only like to apply that live load on that particular corridor. So how can we do so? Well, the first thing I'm going to do is to create a user-defined visibility of only my second level, and I choose that with my selection box, and then I choose visibility by selected objects. I turn back on my grid, and I'm going to utilize this option here to set the origin of the grid work plane to the upper left corner. So now you can see that drawing grid is just located at my second level instead. Okay, so for my live load, I want to utilize what's called a free load. A free load is where you can apply a load to only a partial area of a structure. We can utilize a new free rectangular load. Now, the advantage of a free load is that we can project it onto multiple surfaces. So let's say you have a multi-level story building and this live load corridor occurs on every level. Well, at the click of a button, by leaving these set to all surfaces, we can project that down onto every single level. For today, I want to graphically only select the upper surfaces to apply this to. It will be applied in the global Z direction. The magnitude will be set to negative 0.02 kips per square feet, and then I can graphically select where this corridor should occur. So my first click is going to be on the left side of the structure, and my second click is on the right side of the structure. My coordinates are automatically populated. I click OK. And so now you can see that live load applied only to the particular corridor along that second level there rather than the entire surface. So I can turn off my drawing grid. We can cancel out of this visibility mode to see both live loads acting together here. Okay, so for the wind load scenario, under the Tools option, Generate Loads, from snow loads and wind loads. These are a couple of load generators, but keep in mind that we do have the ASCE 7 here. It really is only applicable for rectangular type structures such as this. The minute that we get outside of these geometric properties, then we need to manually apply the wind loads instead. So we're certainly outside of this realm for our example today, so we cannot use this generator. I also wanted to mention that we're currently in development with a standalone program called RFlow that will essentially apply wind currents to structures, and will integrate with RFEM to bring in those wind loads into the main program here. So it's like putting your structure into a wind tunnel. So hopefully we plan to release that within the coming months. It will be extremely beneficial for specialty structures and odd geometries. For today, I want to just apply a very simple line load to these diaphragms. So we will select a new line load up in my toolbar, and the direction will actually be the global X projected direction. The magnitude here will be 0.2 kip per feet. So what this allows me to do now is to click on these concrete surfaces and to apply this lateral load at those exterior line edges. So again, a very simple application for today. In reality, we'd want to apply different loading scenarios for wind to our structures. Okay, so now that we have applied all of these loads, we can cycle through the different load combinations to see the dead, live, and wind acting together on our building. And once we're fairly certain we've completed the loading, we can go to calculate all. So what the program will do is to run a nonlinear analysis accounting for big P delta and little p delta for both our load cases and our load combinations. So once we are done running this calculation, the results will be presented to us directly within RFEM. Now keep in mind, this is the analysis results only. So once this is done, we can turn off our loads and we're immediately presented with our deflections. Now under the display tab, I had mentioned the results tree. Under deformations, right now you'll notice that our members are denoted by just a single line element. Well, we can change this to colored cross sections instead. We can even smooth the color transition here to make it look a little bit nicer, and we can cycle through these different load combinations to see exactly how our structure is reacting. Under our panel here, we can decrease the deformation factor, but this just gives us a sense on if we accurately applied these loads to our structure and if we're seeing exactly what we would expect under the applied loads. So back to our results tree here, the deflections are nice, but we are also interested in our member internal forces. So I can activate this tree, and maybe I zoom in here to display my rib members and a few of my columns. I can activate the axial forces, for example, which would be important for our column design. We can take a look at shear forces, which would be more important for our rib design. We can look at bending moments for the strong axis as well as the weak axis. For any one of these members, we can always right-click to view the results diagram. So what this gives me is information on the internal forces and deflections that I can activate or deactivate along the member length in a bit more detail. We can even scroll through to the different load combinations and load cases. We can add this to our printout report. We can export directly to Microsoft Excel. So this might be important information if we wanted to do design outside of RFEM. In a similar manner, we have our results for our surfaces here. So again, what you're going to be presented with are internal forces for moments. We have our shear forces, for example. We have axial forces, and this would be the information that we'd want to, again, utilize for design of these concrete surfaces. We also have support reactions, of course, for all of the different load combinations. Now, all of this information is available to us in table format as well. So you'll see here under the node support forces, well, this would be our nodal support forces that we're viewing within the background here. Notice everything is synced up with RFEM in the background, so you'll know exactly which support reaction you're looking at. Same thing with member internal forces. I can click on anywhere within this table and the program will automatically show me where that controlling internal force is within RFEM. So again, you can export this to Microsoft Excel for design with your own tools. So that is a clear distinction of what RFEM alone is for the analysis portion. But now I want to show you a design within the add-on modules. So what we'll start off with is design here of one of our steel trusses. So I'm going to orient this model and to highlight my steel truss here with my selection box. And I'm going to create a visibility by the selected view. So you can see here that only the steel truss is selected. I can right click to turn off the hidden objects in the background, and now we have a nice view of only that steel truss. I would like to design these web members and the top cord. Now notice the top cord is broken into smaller segments here, but that's not a problem. We can design this as one continuous member with what's called a set of members. With the truss generator, the program places a faint dotted line here around all of those segments to create what's called a set of members, and we can design that within the add-on module. You also can select multiple segments, right click, and create a set of member yourself. So I'm going to launch the add-on module RF-STEEL AISC. Now all of these add-on modules are also available in the drop-down box here, maybe categorized a little bit better if in case you can't find anything in particular. For this, we will go to the steel and launch RF-STEEL AISC. Now I do want to preface that I will just touch on these add-on modules. I have done webinars in the past completely devoted to the AISC module. The CSA steel design module is very similar, so by all means visit our YouTube channel and view these older webinars, which will give you in much more detail how to go about steel design. Same concept with concrete design in just a minute, or any of the other topics within our program. So what we want to specify here within this add-on module, I want to just let you know that the add-on module is just a simple dialog box within the main program RFEM. We don't have to remodel anything. We don't have to specify materials, cross-sections, loading. That's all brought in from the main program. The only thing that we're doing here is specifying a little bit of information that's specific to the AISC standard. So for example, we want to choose LRFD design according to the 2016 standard. And as I mentioned, we want to design these web members here. And sorry, one second. We'll choose these web members with our dialog box and I click OK. I do want to design a set of members here. So again, we can design this top cord as one continuous member with what's called sets of members. I choose my LRFD load combinations for ultimate limit state design, and we can check deflections as well. So we move our ASC load combinations under the serviceability limit state design over to the right. Then it's really as easy as just moving down this list. So again, the materials are brought in from RFEM. We don't need to adjust anything here. The cross sections, same concept. We can optimize cross sections within this dialog box, so you can choose that option here if you did want to optimize after the initial calculation is run. Intermediate lateral restraints. This would be our top and bottom flange bracing. So we want to assume for our top cord here that perhaps the roof deck might be bracing the top flange only. So we can set this by first going to this option down here at the bottom, set input for members. And instead of choosing all here, this allows me to select multiple members, which I can do so graphically. I click OK. Then I can specify a lateral restraint But notice in this drop-down box, I want to set this to the upper flange only. So this little picture over here updates, and we're going to assume that our roof is maybe screwed in at every 1 foot spacing. So we add in enough intermediate lateral restraints here to account for essentially that spacing of the upper flange only, and you'll notice that it's populated for all of those members at once. So instead of having to individually go in there and specify that for each member, we just took care of all of them. Now, the rest of the members here would be my web elements. Now, notice that the table, again, is synced up in the background so I can see exactly which member I'm looking at. We don't want to apply any lateral restraints for our web members. The effective lengths for both the members and the sets of members. This is going to be the unbraced length for buckling about our strong axis, our weak axis, flexural torsional buckling, effective length factors. So all of these can be accounted for, adjusted here. The program will default to the full member length. Now, the lateral torsional buckling, this is something that's a little bit more unique to RFEM, is that we're actually going to run an eigenvalue analysis in the background. What this allows us to do is to determine the buckling mode shape and the critical moment before that buckling mode will occur. So it's definitely a more advanced approach to lateral torsional buckling, but can be much more cost effective and theoretical approach. So again, my previous webinars cover this in quite a bit more detail. So today we'll just leave everything as the full member length. The serviceability data, this is where we can check deflection. So if I'd like to include my web members here for deflection checks, I can graphically select them once again. You'll notice that the length defaults to the full member length. I also want to choose my sets of members for my chord element, and I click OK. Now, underneath the details settings and under the serviceability tab, this is where we set our limiting deflection ratio. You can see it's set at L over 360 by default, but by all means you can come in here and adjust this accordingly. So now that we have completed all of the input data within this module, we're finally ready to run our calculation. Now notice that this solves within a split second because we already have all of the internal forces from the RFEM calculation. So we're just simply bringing them into this add-on module, applying the AISC equations, and then ultimately we're going to give you a code check. So we're presented with our results table still within this add-on module. Notice you can view design by load case, design by cross-section. In this particular instance, we only have 2 cross-sections. We can view design by sets of members or design by member. As we pull down the add-on module, notice that everything is synced up in the background. So as I'm clicking within this table, you'll notice the member I'm looking at is highlighted, and that red arrow refers to the controlling internal force for that particular check. Now, even more so, I also want to point out that we're going to give you a complete check within the AISC, meaning you'll notice that we have every chapter listed here. So not just the controlling chapter for the design ratio, but you'll see here for this member, for example, chapter F for yielding, local buckling, lateral torsional buckling, we have shear checks, we have serviceability. So there's never any question about, well, I think that one code check should be controlling in this particular chapter, but the program's telling me that something else is controlling, when everything is listed here available for your review. Even more so, you'll notice that we can expand these trees. We can see how the member was classified, whether it's compact, non-compact, slender, non-slender. All of the code references are listed here, and all of the variables. So again, very transparent in where the numbers are coming from to avoid that black box type of program. Now, by all means, you don't have to print off all this information. If you're even interested in just seeing the controlling design ratio for each member, you can filter here by selecting the max and then hitting the filter option. Now for each member, you're only going to see for both ultimate and serviceability limit states the controlling design ratio. So all of this information is available to us to export to Microsoft Excel for further sorting purposes. The one thing that I did want to point out, remember that I mentioned the eigenvalue analysis for lateral torsional buckling. Well, if we take a look at the stability analysis here for our results within this particular member shown in the background, this is for our top chord set of members that we designed. We have this option for the stability check to view the mode shape. So I can zoom in here, perhaps I can decrease this factor just a little bit. This is the buckling mode shape for lateral torsional buckling that the program has calculated. So ultimately with this mode shape we're going to come up with the elastic critical moment for lateral torsional buckling listed here. So a little bit more of a theoretical approach rather than just using the general formulas from the AISC to come up with this value. Now ultimately you're going to have quite a bit more control over intermediate lateral restraints, and this will be accounted for with this theoretical approach. So maybe we get a slightly higher capacity here than what we'd normally see with just those typical analytical equations. Now, all of this information is available to us graphically back in RFEM as well. So if I hit the graphics button here, I'm brought back into RFEM. Now notice I'm still technically within this add-on module here, RF-STEEL AISC. I'm just viewing my design results, my design ratio back in the main program. So perhaps under this panel, we decrease our member diagram. So you'll see where the controlling ratios are for ultimate limit state, as well as we can turn on for serviceability limit state, which you can see here is quite low. Under the display options, as we saw before, we have our results tree here. Well, under the members tree, we can actually change this to without a diagram. So maybe we want to see just colored lines here, or we can change it to colored cross sections and use this in conjunction with our color panel over here on the right. Again, you can add all of these pictures to your printout report for your design per the AISC. Okay, so let me cancel out of this visibility mode. I'm going to turn off my results here, and we will go back to the normal view of our entire structure. So the final module that I want to show you is the concrete module, and we can see that within RF concrete members. So we can launch RF concrete members here within our project navigator, and you'll notice that this dialog box looks almost identical to RF-STEEL AISC. So once you get a handle on one module, all the modules have the same look and feel to them, of course, with just some variability depending on the material or the specific design code. We select the ACI 318. You can see here the CSA A23.3 is also available. We choose our strength limit states. Our strength limit state tab, we want to choose our LRFD load combinations and move them over to the right-hand side. The serviceability, we can choose our ASD load combinations and we'll move those over to the right-hand side. So under the materials, again, this information is just all brought in from RFEM. We have our cross sections, again, brought in from the main program. Our rib elements are also brought in here, so we can design the reinforcement for the effective widths here of our concrete members as well. We won't be doing that today, but just keep that in mind. Under the reinforcement table, so this is what allows me to define the different rebar requirements for my design. For example, for this particular member, I want the program to optimize here on which bars, either number 5s or number 6s, it should implement in order to meet the design requirements. The ties and stirrups here, we want the program to choose number 4s. Now, I want to also mention that we're not going to design all of these members here, which you can see by default is set here. So we can clear out these selection boxes, and instead I'm going to graphically choose only my first 2 column members here. So now the program will utilize these longitudinal and shear reinforcement stipulations in order to design our column members. The reinforcement layout is important too, because for our columns we want to change this to uniformly surrounding for biaxial bending. The program will design the internal forces and relate this to the reinforcement design for axial loads, shear loads, moment, and torsion. The next couple tabs are really just specific to the AISC. So some default settings are within here. It'll adjust reinforcement spacings, maybe minimum reinforcement requirements according to the ACI standard. And finally, we have our serviceability tab. So we can design according to crack width. We'll let you know if you are exceeding the crack width based on the value set here within this drop-down box, which is set by the ACI committee. Maybe we want the limiting crack width to be 0.12 inches. We also can take into consideration spacing considerations of the ACI reference in order to limit crack width based on our shear spacing. So the program can also account for that. We can activate the deflection here. So you'll notice I now have a new deflection data table. Again, this is similar to what we saw within the AISC module. We're just going to limit this to the deflection ratio of L/240 for our concrete members. So in a similar manner, we click calculate. Again, those internal forces have already been solved for. It brings them into this add-on module, and the program needs to determine, based both on the ACI requirements as well as just our required forces on the member, what the reinforcement should be designed for. So the required reinforcement is given here by member. And more importantly, though, we'd probably like to see what the program has provided for the reinforcement. So with this, we can see that member number 2, which is our upper column here, is going to be specified with number 5 bars oriented around the face. Well, when we take a look at the lower column here, we're going to have significantly less reinforcement, of course, because our loads are relatively lower. So that's what the program's doing. It's essentially taking the required reinforcement, and then it will produce the provided reinforcement based on the reinforcement data that you have selected back on the previous tab. We will check serviceability as well. Again, that's including that crack width. It's also including deflections, and we'll give you a ratio check here. We can view this information graphically back in RFEM just like what we saw with our steel members. So maybe I create a user-defined visibility with only my 2 columns here, and I can zoom in. I'm right now currently looking at the required reinforcement. So this is based on the applied loads. Now, if I overlay on this the provided reinforcement, this is what the program has determined that it can implement into these columns in order to meet the required reinforcement. So inevitably, the provided is greater than required, which is what we should see graphically here. You also have the option to turn off these graphs and to turn on the reinforcement rendering. So this might be nice if we cancel back out of our visibility mode here, just to see how this ties into the rest of the structure. So that really is a quick introduction to concrete member design. Of course, we can also design these surfaces for reinforcement, but again, many other YouTube channels related to ACI design that would be relevant for a much more in-depth design introduction into these add-on modules. The final thing just to show you guys is the printout report, which we can access this within our table up here, our tools. We can go to current report printout. Now the program does have a few default options for a template, so we can take advantage of this, but just know that you can create your own report template as well. So once you have your report set up the way that you would like for all of your projects, you can go up here to settings and to save a new printout report from your current printout report, and that way you don't have to adjust the data every time. So you'll notice that a completely separate application opens up here. We have our table of contents located over on the left. As we click on these different table of contents, the program will sync that up to whichever table we want to view here within the printout report. Now, if I collapse these trees, the program's also putting all of our design result information from our add-on modules here. So this includes a few pictures from RF concrete members. So keep in mind that although these couple of pictures were implemented within the printout report, by all means you can add pictures which will automatically be updated if any changes take place within the model. If by chance you don't want any of this information within the printout report, for example, nodes, maybe that's not of interest to you, you can always right-click to remove from the printout, and then the entire printout report will automatically refresh once you make those changes. Under the settings, or sorry, under the edit selection, this will be the ability to turn on and off all of the different input data and output data for your model for the printout report. So like I said, once you get this set up the way that you'd like, maybe you add in your own header with your own company logo here, you can save a template and utilize that for all future projects. So that will conclude our webinar today. And as always, I know that was an incredible amount of information. You can always visit our website at dlubal.com to learn more about RFEM, the program, as well as the different add-on modules that we have available. You may be wondering about pricing as well. Well, we're completely transparent with that on our website. You can visit the web shop, which is available at the top of the screen, to view all the different add-on module pricing as well as RFEM. I always want to encourage everyone to follow us on our social media sites. For example, I mentioned our YouTube channel multiple times. This has recorded webinars such as this one, as well as short videos that might be useful for training and learning purposes. We'll also let you guys know when events and conferences are taking place, as well as technical articles, frequently asked questions. So just a quick way to access this information on those social media sites. If you have any questions about today's presentation or anything else, feel free to contact us at our Philadelphia office at info-us@dlubal.com. Again, that's info-us@dlubal.com. Our phone number here is 267-702-2815. We will have many more upcoming webinars. As I mentioned, this is a 3-part webinar series. So webinar 2 will be taking place on July 31st. Webinar 3 will take place on August 20th. You can register on our website at dlubal.com under Support and Learning Webinars. As most of you know, I send out a reminder email about a week before this will take place, so feel free to register through there as well. Many of you will want PDH certificates for today, and that's great. They will automatically be emailed to all participants for today's webinar. This is restricted to people who were available for the full presentation, just simply because that's a requirement of the states that we are allowed to provide PDH certificates for. If there were any attendees who watched with maybe a colleague today and you yourself did not register for this webinar with your own name and your own email, you will need to request a PDH. So you can do so at info-us@dlubal.com. So again, if you yourself did not register for this webinar, feel free to go ahead and send in a PDH request to this email address shown here. And with that said, I want to thank everyone for attending today, and as always, I hope to see you at our next webinar. Thank you.